Hello everyone, and welcome to this class on first derivative analysis, which will then flow into the discussion about the second derivative analysis. Now, this is a topic that I'm fairly sure you're very familiar with because it's one of the topics that is emphasized in high school, in your high school calculus course. And in my experience, students usually have fairly clear understanding of what these the basic ideas of first and second derivative analysis. So our task here will be, as usual, to make sure that your understanding of this topic is even stronger, and we're going to go into some technical details. We'll start from the first derivative, and as you most likely remember, the first derivative, being the slope, tells us whether the function is going up or down, which is what these three arrows are meant to signify. So let's first of all review the basic concepts related to that. So if we have a differentiable function f of x, so at any point where the derivative of the function is positive, well, what's the derivative? The derivative is just the slope of the function. So if the derivative is positive, it means that the slope is positive, and therefore the function is going up. However, it can go up with different patterns. For instance, we see up there two different options where in one of which the concavity is down, the other one is the concavity is up. But we're not looking at the concavity yet. So just look at those two graphs as a reminder that the function can be increasing, but with different patterns. Similarly, if we have any points where the first derivative is negative, that means that the slope is negative, and therefore it means that the function is going to be decreasing. Okay? So that takes care of the situation where the derivative is positive and is negative. Now let's look at some more details about this particular concept. Okay. Now, first of all, a little bit of a terminology with which you're still going to be fairly familiar, I suppose, I assume, and I hope, and I trust. So if we have a point, a c, f of c, which is on the function, we're going to say that it is an absolute maximum of the function if any other value of the function is less than or at most equal to that one. Okay, so in other words, this is the topmost point on the function, the one which is highest on the graph. And similarly, we can talk about an absolute minimum where the point is actually at the bottom. So the absolute maximum will give us the peaks of the function, and the absolute minimum will give us the troughs, the valleys, the bottoms. Okay. But again, we're talking about absolute maximum or minimum if these are the highest points overall. Nowhere else in the graph of the function can the function be higher than the absolute maximum or lower than the absolute minimum. It can be equal, so you may have several absolute maximum minimum, but should all be at the same level. Now, sometimes we need to refer to both absolute maximum and minimum together, in which case we're going to talk about an absolute extremum in the singular or extrema in the plural. So this is a Latin word or word from Latin, so it has a strange plural. So we're going to, when we put together both maximum and minimum, we're going to talk about absolute extrema. Now, sometimes you're going to also have to distinguish between an extreme point and extreme value. So the extreme point, of course, is a point. So we're going to talk about both the x and the y coordinates. So we'll be talking about c and f of c together. On the other hand, if we're talking about the extreme value, we're talking about the value of the function, which is the y coordinate. So in both cases, we need to clarify, we need to be careful about what it is. If you have a question about this and you're not sure whether we, being me or the book, are referring to an extreme point or an extreme value, as usual, ask and make sure that you clarify what is being asked for. But remember, sometimes there may be a little bit of, not confusion, but a little bit of sloppiness in the terminology here. Now, let's look at some more concepts related to that. Sometimes we're going to talk about the relative extremum instead of an absolute extremum. Okay, and what's a relative extremum? Well, that's just a point which is an absolute extremum as long as we just stay close to it. Okay, so for instance, let's look at this function that the function that is that corresponds to this graph. Okay, so if we look at these 2 points, neither of them is actually the absolute minimum, because in both cases the function actually goes even lower than that on the right hand branch here. Okay. However, if we simply focus on a little interval around each of these 2 points, so here or here, we can see that each of these 2 points is its own absolute minimum in that little interval. And therefore, we're going to say that these 2 points are relative minima. Okay, so it's sort of like these guys are the provincial champions instead of being the national champions. In a similar way, these 2 points are not the absolute, neither of them is the absolute maximum of the function. The function keeps going up to the left here and it reaches higher levels. However, each of them is the maximum in its own little interval, and therefore we're going to talk about these ones being relative extrema. Here is another piece of terminology that you're most likely familiar with. If we have a point on the graph of a function where either the first derivative is 0 or undefined, then we're going to say that this value c is a critical value or a critical number for the function, and that the corresponding point is a critical point. Okay. Now you may remember that just a few minutes ago we looked at what happens when the derivative is positive and then when the derivative is negative. Now we're looking at what we say when the derivative is 0 or undefined. Well, think about it. There are no other options. Okay, so that's it. So either the derivative is positive or it's negative or it's 0 or it's undefined. So in each of those cases we can tell exactly what it is. Except for one thing. We've actually given a name to the points where the derivative is 0 or undefined, but I haven't told you yet what happens there, right? And so here is one thing where we want to be a little bit careful, because probably in your high school you have been allowed to be a little bit sloppy on this issue. So we're going to look at that issue a little bit more in detail. So let's see, there are 2 important theorems to remember when it comes to analyzing the first derivative, and also when it comes to understanding what happens at its critical values. The first one is the following. First of all, and this is called the extreme value theorem. This value says that if a function is continuous on a closed interval, means it's continuous all the way from the left endpoint to the right endpoint, then it will certainly have an absolute maximum and an absolute minimum on that interval. Okay, sometimes those absolute extrema are going to be found at the endpoints, okay, but they're certainly going to be there. Notice this is what we call an existence theorem. It tells us something exists, namely the absolute maximum minimum. It doesn't tell us how to find it. Okay, so this is an existence theorem only. And again, we're not going to go through the proof of this one, although intuitively you can think about it. Remember, this is a function that starts at a definite value a, and a and b, remember, they're not infinity, okay, because you cannot have a closed interval that starts or ends at infinity. So we're starting at a certain point and we're moving on to another point that corresponds to b. Well, that means that the function has got to reach a highest value somewhere and it's got to reach a lowest value somewhere else. Intuitively, it's fairly clear. The technical proof a little bit more convoluted. Another important theorem is something called Fermat's theorem. Fermat, of course, is a famous French mathematician, and his name is attached to this theorem. And this tells us actually how to find the maximum or minimum. It says if a function has a relative maximum or minimum, notice we're talking about relative here, not absolute. Okay. Anyway, if there is a relative maximum or minimum at a point, then c is a critical number for f of x. What does that mean? It means that the derivative at that point has to be either 0 or undefined. Okay. Now notice that this is a one-way theorem, okay? So it's not an if and only if. It tells us if we have a maximum, then c has to be a critical value. It does not tell us that if you have a critical value, you definitely have an extremum. You may have critical values that do not correspond to any extremum. Okay, so you may want to be careful about that. So of course, as usual in class, we're going to be looking at some examples that we're going to apply these 2 ideas. But again, keep in mind 2 important things. The extreme value theorem is an existence theorem, so it tells us only that something exists, it doesn't tell us how to find it. Fermat's theorem, first of all, is a one-way theorem, but it's also a theorem that is more operative in the sense that it tells us how to find those extreme values. It tells us that if we want to look for them, we better look only at the values where the derivative is 0 or undefined. Now, let's see how we can put together all this information to determine the up-down pattern of the graph of a function. And again, this is something that you should probably be very familiar with. We're going to, in class, to spend some more time making sure that we know how to put it into practice, into action. Okay, so what we're going to do is, first of all, we're going to compute the derivative and we're going to find the cut points of the equation f prime equals 0. Now remember, the cut points are the values where f prime is 0 or undefined. So they're going to be almost critical values, except for a critical value we need also that value to be a value of continuity for the original function. Okay, so we find the cut points, and that tells us where possibly we can have critical values and or discontinuities. Then what we're going to do is we're going to solve the inequality f prime greater than 0. This is going to tell us in the remaining part of the graph, so once we have identified where the derivative is 0 or undefined, in between those values is the function going up or down. So that leaves us one last thing to do, and it is to use this pattern and any other information about that we have about the function, information about continuity, asymptotes, limits, and so on, to classify each critical number as being a maximum, a minimum, or something else. Okay, so this is the first derivative analysis. It gives us a full picture of what's going on with the function in terms of going up, going down, having a maximum, having a minimum, having something else. And this is the analysis that I expect you to do for every function that we're going to be doing in class as well. Now, there is also something called the first derivative test. Okay, this is a classical test. You're probably going to find it in any traditional and commercially available textbook. But this is a limited kind of thing. It's a little bit less than the full first derivative analysis I just mentioned. The first derivative test only tells us how to classify critical points. So only gives us the last bit of the analysis. Just tells us how to figure out whether a critical value is a maximum, a minimum, or something else. So it is a limited kind of operation, and I would definitely expect you to always perform a full first derivative analysis so you can find out everything you need to know about the function in terms of the up-down pattern of it.